All right, let's jump right in. We hear all the time about AI being this incredible, all powerful learning machine. But what happens when it just doesn't learn? What happens when it stares at a mountain of data and completely, totally misses the point? Well, that's exactly what we're going to dig into today, the surprisingly common problem of underfitting.
So, it really all comes down to this one big question, right? Why on earth do some of these super sophisticated models just fail? And I mean, fail badly at the one thing they are built to do: learn from the data we give them. The answer? It's all about a fundamental mismatch. Okay, this right here, this is the perfect way to picture the problem. On one hand, you've got the data. That's reality, right? It's complex, it's messy, it's full of all these amazing details. But then, on the other hand, you have your tool, the AI model. And in this case, it's just way too simple for the job. It's kind of like trying to paint a masterpiece with a big, blunt crayon. You're just never going to capture all that richness.
And that, my friends, brings us to our big word for the day, underfitting. That's the technical term for what happens when a model is just too simplistic. It's too basic to really get the underlying patterns in a data set. And it's so important to understand this. It's not that the data is wrong, it's that the model itself just isn't equipped to see what's really there. Okay, so how do we actually diagnose this problem? Well, in the world of machine learning, it all comes down to two key symptoms that together create something called the bias and variance trap. So here they are. An underfitted model has high bias and low variance. Now, what does that actually mean? High bias is simple. The model is just making the wrong assumptions. It's just plain wrong about the data. And low variance? This one's a little tricky. It means the model's predictions are super consistent, but they're consistently wrong. Think about that. It's stubborn. No matter what you show it, it just keeps giving you the same bad answer.
I know, bias and variance can sound a bit academic. So let's make this crystal clear with an analogy. I want you to imagine a really unique, kind of messy, jagged splash of ink on a piece of paper. You know, the kind where every little splotch is different with all these random, interesting shapes.
Okay, you see that ink splash? Now your job is to trace it. Simple enough? But here's the catch. The only tool you've got is this rigid, perfect circle stencil. You can already see where this is going, can't you? The tool is just completely wrong for the job at hand. And this is where it all clicks. Think about it. No matter which crazy ink splash you try to trace, that stencil is always going to produce the exact same perfect circle. That's your low variance. It's consistent as heck. But it will always be a terrible, awful representation of the actual ink splash. And that right there is your high bias. It's consistently, stubbornly wrong. The official name for this whole problem, it's called model rigidity. It's a great term, actually. It just means the model is too stiff, too inflexible to bend and adapt to the true shape of the data it's supposed to be learning from. So let's look at a super classic example of this. You can see the data points here, right? They're clearly forming a nice curve. The pattern is obviously not a straight line. But look at our model. The model we're trying to use here is a simple, linear one. All it knows how to do is draw straight lines. It's like this stubborn, rigid line trying its best to describe a beautiful, flowing curve. It's never going to work, right? It's got that high bias because a straight line is a terrible assumption for this data. And it's got low variance because it's just going to keep drawing that same wrong line over and over again.
Okay, so we have diagnosed the problem. But what does this actually mean in the real world? Like, so what? Why does this matter? Well, it matters a lot because an underfitted model completely, utterly fails to do the one thing we need it to do: generalize. And this chart is basically the model's report card. And it's not good. Look, it performs poorly on its training data. That's the stuff it was supposed to be learning from. And then, no surprise here, it performs just as badly on new data it's never even seen before. It's like it never even went to class, so of course it's going to fail the final exam.
So here's the bottom line, the most crucial point of all. An underfitted model is, for all practical purposes, useless. It isn't just a little bit off, it's fundamentally broken. It is incapable of making accurate, reliable predictions about anything. You just can't trust it because it never really understood what it was looking at to begin with.
But hey, it's not all doom and gloom. The really good news here is that this is a totally solvable problem. There's a clear treatment plan, a set of 3 really effective cures for underfitting.
All right, here we go. Cure number 1, increase the model's complexity. This means giving it more things to think about, more features or parameters. It's like giving it more dials and levers to play with. Second, you can just switch to a better tool. Ditch the simple algorithm and move to a more sophisticated one, like a neural network, something that's actually designed to see those complex curves. And third, sometimes it's really simple. The model just needs more study time, so you just let it train for longer. To make sure these solutions really stick, let's go back to an analogy. I want you to think of your AI model as a map maker, and their big job is to create a super detailed map of a huge, complex mountain range. Now, an underfitted model, that's our map maker, but they've only been given a blunt crayon and a tiny little notepad. Not gonna work. So, let's see how our cures help this poor map maker. Increasing complexity, that's like taking away the crayon and giving them a set of fine-tipped pens and a much bigger canvas. Now they can capture all the tiny details. Switching algorithms, that's like telling them to stop drawing a flat 2D map and instead build a full 3D topographical model. It's a whole different, much better way of seeing the mountain. And extending the training? Easy. We just give our mapmaker more time out in the field to explore every peak and valley. All right, so when we put this all together, what's the big lesson here? It all comes down to finding that perfect balance of complexity. You don't want a model that's too simple, but as we'll see, you don't want one that's too complex either. So let's do a super quick recap of what we've covered. We learned that underfitting happens when a model is just too simple. We know it's defined by that killer combo of high bias and low variance. We know that leads to poor performance pretty much everywhere, on data it's seen and data it hasn't. And most importantly, we know how to fix it. Make the model more complex, or just give it more time to learn. So it's clear we need a model that's in that just right zone. You know, complex enough to get the job done, but not so simple that it misses the whole point. And that leaves us with one really fascinating question to chew on. We've just figured out how to fix a model that learns too little. But what happens when a model goes to the complete opposite extreme and learns too much? That sounds like a great topic for another time.